Okay, let's go ahead and get started, everyone. Welcome to today's webinar, Demystifying How Artificial Intelligence and Machine Learning Can Be Used to Improve Building Performance. I'm Jessica Granderson from Lawrence Berkeley National Laboratory. I want to acknowledge my team here at LBL. This work was in collaboration with Hannah Kramer and Yimin Chen. A couple notes of housekeeping. We certainly welcome your questions and comments throughout today's prepared remarks. We will address those at the end and open up for a little discussion and Q&A, but do enter your thoughts as they occur to you. I'll ask for Hannah's support in monitoring those questions as they come in. She'll be able to interrupt me for any really big points of clarification that I should stop to address. Next slide. We'll cover 5 topics today. We'll get started with an introduction, followed by review of AI and machine learning. Then we'll get into common methods, followed by machine learning applications in commercial products, and we'll wrap with some conclusions and then that Q&A and discussion section. Next slide, please. Just a brief introduction to get us grounded next. There's 3 objectives for today's webinar. The first is to identify the latest machine learning and AI techniques that are used in market deployed energy management and information systems technologies. Those are our advanced meter analytics technologies, fault detection and diagnostic tools, and advanced or predictive optimization on the control side of things. Second objective, raise awareness about what the emerging techniques really are and their role specific to building operations and continuous energy management. And finally, to really surface some of the strong points of potential as well as challenges in integrating these techniques into practice. Next. It's always important to highlight explicitly some of the overarching context that's motivating our interest in exploring AI for the buildings industry. And I'll make really 3 main observations of relevance here. First is that the operation of our buildings is becoming a lot more complex as we diversify supply side sources, as well as look behind the meter to increased integration of distributed energy resources. So we're very actively these days talking about things like value stacking, energy arbitrage, making our buildings grid interactive, and deploying real resilient strategies for building operations with increasing attention to health as well. All of this is requiring more reliable, more sophisticated control and diagnostics of our building controls. Second, we've seen a lot of advances in things like IoT, networking, cloud-based delivery of various applications, even data acquisition and management. And that's all kind of converging to make it possible to bring building science data science to the buildings industry. Third, the acceleration of really successful machine learning solutions in other commercial domains is sparking for us this whole flurry of activity in the buildings community. Now, some of that activity is really grounded, solid, robust, and some of it is kind of more on the aspirational side or even, into the realm of pure marketing. And it's some of that nuance that we want to dig into a bit today. Next. So I want to give us a short review next, please, of AI and machine learning from a kind of high level. As far as definitions go, we're hearing all the time terms like AI and machine learning, and now more frequently deep learning. And I think for the purpose of today's discussion, we can kind of stay high level and characterize AI as a field of science that is aiming to develop computers that are capable of replicating human behavior and decision making. And if you think about that over time, this has really become a moving target. We keep increasing the bar as new advances are brought forth. What we thought of as artificial intelligence, say in the 1970s, looks quite different from what we think of today. Now, machine learning is a subset of AI that focuses on developing algorithms that can learn from data without being explicitly programmed to accomplish a very specific objective or outcome. If we think about deep learning, that's then a subset of machine learning that's applying artificial neural networks with many, many layers. That's the deep part of deep learning, to excel at very specific and certain types of learning tasks. I think if we just keep that overall organization in our mind, that we're really talking about things that are subsets of one another, that can give us a sort of helpful grounding from which to continue today's discussion. Next. Here, we wanted to put together some kind of graphic because it's really fun to look at some of the key historical milestones over time from the AI community, and to place those kind of alongside what we've seen in buildings, and to look at that temporal kind of retrospective. So in the 1950s, we had Turing and McCarthy really kicking things off, establishing seminal work for the AI field. And buildings in that time period were, of course, controlled pneumatically. Throughout then the 1960s and 70s, the AI field started bringing forth solutions like neural networks, genetic algorithms, and even early navigation work. It's kind of grayed out there, but we've called out the Stanford Smart Cart. Through the 1980s and 90s is when we started to see that DDC evolution in buildings, with big uptake of the BACnet protocol and centralized building automation building automation systems. And it was during that period in AI when we started seeing things like Bayesian networks, and a lot of folks will remember the Deep Blue chess champion. By 2000s, further advances in things like speech recognition. We moved past chess into AI-based Go competitions. And on the building side, we saw acceleration of EMIS technology encompassing meter analytics, fault detection and diagnostics, and predictive optimal control. Next. Now today, some of our most visible, kind of familiar examples of AI in commercial products are, not surprisingly, coming from the social networking and e-commerce industries. We'll get into some very specific methods next, so I don't want you to, worry too much about unfamiliar terms in the blue boxes here. But I want to share a couple of the many examples that are proliferating through these industries. Companies like Amazon are using machine learning to do things like tag reviews as either positive or negative, further leverage those labels for additional mining and processing specific business insights. LinkedIn is doing rankings and kind of a recommendation system to connect job seekers and job providers. YouTube's using machine learning to kind of get us down those rabbit holes of continuously clicking on video after video, really driven through quantitative estimations of viewers' quality of experience. And we could go on and on with these examples, but the point is that we're experiencing this in a lot of the technologies that we're very familiar with and daily, if not weekly, users of. Next, please. Here we'll start introducing some of the actual common machine learning methods next, as well as how they're being used in building analytics and control applications. So allow me a moment to really walk folks through this slide here. Generally, machine learning methods are categorized as supervised learning, shown on the left, or unsupervised learning techniques, which are shown on the right of the slide. Now, life is never that straightforward, so there's actually two other categories, semi-supervised and reinforcement learning, but I'm not really going to cover those today. In supervised learning on the left-hand side of the slide here, the whole objective is to predict something, some class or some value, in a context where we actually have labeled data that gives us the answer that we're seeking. And we can use that to train models or algorithms to get the answer for new cases where we don't have the labeling available. Now, in some unsupervised learning, we don't have that. We don't have any labeling or predetermined information that can ground our learning solution. And we're really focusing on determining patterns or groups in our data sets. Let's give a couple examples. On the supervised side of things, there's two major classes of methods. Regression, which we're already pretty familiar with, so I'll kind of pick that up later, and classification. And I'm giving just a toy illustration here of classification. We might be presented with data that covers many different types of, let's call it, fruits. Since we have labeling, we could train an algorithm to learn to identify which fruits are, say, bananas versus something else, so that when we're confronted with a new tranche of data, we're able to automatically make that assignment. These are bananas, these are other things. Now, moving over to the unsupervised side, the two major classes of methods are going to be dimension reduction and clustering. Dimension reduction, kind of like the title implies, is really about minimizing the variable space or the order of complex functions. And I'll give some examples for buildings of that a little later. Now, in clustering, we could use another kind of toy illustrative example. Let's say we have data that represents features of 3 different types of fruits, and we might be able to, through a clustering algorithm, correctly group them into those that are apples versus bananas versus peaches. So we wouldn't have the labeling of that ahead of time. We would just recognize through their features, their shape, their color, their texture, and be able to make those correct assignments into those different categories. These are, of course, just some, kind of playful toy examples. So let's go ahead and dig into some more concrete building-focused illustrations of these techniques. Next, please. In the next several set of slides, I'm going to cover general concepts of the 4 key classes, along with common method types that you may have heard of to implement these classes of strategies, and some examples. And I want to make the distinction that these examples are drawn from the literature on how these techniques are being used specifically for buildings applications. In the next section of content, we're going to cover not just things from the literature, but example of applications that are actually being integrated into commercially available product offerings. So first, regression. This has been, of course, very heavily used in the buildings industry for decades. So, buildings folks, we actually have very deep, albeit narrow, expertise in machine learning already. Regression is a set of statistical processes for estimating relationships between dependent variables like, say, building energy use and independent variables like temperature or time of day. Methods that you may have heard of: linear, nonlinear, multivariate, or logistic regression. And the applications are really centered around prediction of and modeling of load and energy use to do things like anomaly detection or measurement and verification of energy savings, to make predictions for model predictive control, and sometimes used in data cleaning activities. Next. That second big category of supervised learning was classification. In classification, we have kind of broken the world into sets of categories. And we are able to take any new observation and correctly assign it to the categories that we've defined to be of interest. So if ever you're hearing terms like linear classifier or support vector machine, decision tree, Bayes network, even neural networks in some cases, you can map those back to the general concept of classification. So for example, in fault detection and diagnostics, we might classify certain portions of a data set as reflecting faulted versus unfaulted operations. Or we might classify data as coming from a in-term versus summer session, say for schools. And this, or we could use for data cleaning. We might classify data as normal or representing, say, outlier points. Next, please. Moving into the unsupervised approaches, we've got clustering. This is really just all about grouping similar data points. In the buildings literature, this is commonly done with either artificial neural networks, k-means, or expectation maximization clustering approaches. And a pretty diverse set of applications that you can find folks exploring, at least in the research literature. Clustering to tag data from building automation systems, to conduct fault diagnostics or characterize load profiles. You could think about sort of different load shapes that you might observe out of a population, particularly interesting, say, in a utility kind of context. Clustering is often used in optimal control, potentially in human-computer language processing and in data cleaning applications. Next. So finally, we'll move into the last major kind of class or category. This is the dimensionality reduction. Here we're interested in reducing the number of variables that we need to characterize a function or process. Building operations, building controls can be very complicated and the result of a number of different influences or factors. So if you hear things like principal component analysis, independent component analysis, linear discriminant analysis, and you're thinking about buildings work, then chances are that this is in the space of dimensionality reduction, where a lot of times this is a sort of input step to do things like to do feature selection and use that to drive things like BAS data processing, point tagging, fault diagnostics, or optimal control. Next. Now, independent of the specific machine learning method or even the specific application of interest, there is a sort of generalized common workflow that's typically followed to implement and deliver machine learning in our applications. And that starts with collecting data, cleaning data, and training models. And a lot of times, data scientists know the kind of dirty secret that a huge part of the effort, time, and resources are going into these preliminary steps before you really have the fun of digging too far into your data. Once we get models trained, we're validating them before incorporating them into analytics. And hopefully, after some time and experience executing those methods in applications, then we're able to use some feedback to improve the models. Next. I want to move now into a transition and talk about what we found about how commercial products, and next slide please, are actually using machine learning for some of those applications that we saw referenced in the literature. And in the next set of materials I'm going to be presenting is largely based on interviews with a handful of product providers. Now, some of these providers have joined us today, and I want to be sure to really thank them directly for talking with us about their efforts in a way that could really inform some of what we're able to share with you all in today's discussion. And so in these interviews or discussions, we had 3 objectives: to explore, of course, the AI or machine learning based applications that are being incorporated into this technology space, advanced analytics, and supervisory controls. Second, to get the vendors firsthand perspectives on what kind of progress we're making, and to third, identify both benefits as well as barriers in applying these techniques throughout the technology sector. Some of the specific questions we asked included things like, how does any particular organization or technology provider define AI and machine learning? How are those techniques being applied within the products? Is it very, very, very early stage or actually implemented live in buildings at this point of time? And what are the technical challenges? And then we also wanted to understand something about folks' vision on AI and machine learning as we look forward to future directions in the buildings industry. Next, please. As far as process, kind of like how we sifted through the space here, was first thing we did was just review publicly available information from close to 90 product vendors using their websites, brochures, case studies, etc. Just to give you a gauge, we found that 11 of those, that's just over 10%, explicitly noted that they use AI or machine learning in their products. At the end of the day, we interviewed 4 of those. We'd love to go broader. The only constraint here was really just availability, scheduling, resources. Next, please. There were 5 applications that emerged out of these discussions that folks noted that that are applications that their technologies support that do include machine learning methods. So those were load prediction, automated data tagging, data cleaning, control optimization, and fault diagnostics. In the next few slides, we can unpack those a bit more. Next, please. So in the load prediction category, this is using either BAS or meter data to develop a consumption or operational model, and those tend to be used for energy or operational anomaly detection, to be used as for predicting loads in control optimization, or very much the workhorse of measurement and verification, more colloquially known as savings estimation. These tend to be implemented with many different types and flavors of regression-based approaches. The graphic here is an illustration. The purple line would be outside air temperature. The green line, load data used to train a model. The orange line then representing the model prediction of load, and green reflecting the actual metered load. These types of visualizations are useful when you're doing before and after energy savings analyses. The techniques, while spanning different types and flavors of regression, different independent and dependent variables, kind of all boil down to application in pulling out anomalous behaviors, inputs against which to devise advanced controls or foundation of savings estimates. Next, please. So automated data point tagging. Out of the gate, one vendor noted that out of the sort of full suite product delivery, they're spending 70% of their time in the data tagging. This is data coming out of building automation systems, with 30% of the time used for the rest of the energy and fault modeling activities. So the whole purpose here is to really streamline the data integration process in that stage of configuring and training software tools like fault diagnostics. One vendor noted that they're using Bayesian networks to classify those tags, and also mentioned taking advantage of the brick ontology or semantic model to be able to query and better understand, interpret the meaning of the data behind those tags that are being learned. Next, please. Fault diagnostics, we saw machine learning being used in both steps of the process here. So first, folks mentioned that on the detection side, they were using those supervised classification or unsupervised clustering algorithms to identify the presence of a fault in data. When it comes to localizing or identifying the root cause of those faults, that's the diagnosis step, others were exploring inference methods, or things that get into the Bayesian realm of intelligence. Next slide. Control optimization. So there we heard about folks using advanced occupancy sensor networks that generate occupancy data at much higher granularity or resolution than you can get from sort of general occupied, unoccupied schedules. Using that to establish building occupancy profiles, and then building that as an input, combining it with an energy consumption model to inform a supervisory optimization approach that could implement improved optimal start, midday ramps, whatever may prove to be efficient and advantageous given what those actual measured occupancy profiles are. And it's a very dynamic approach that may change, you know, from day to day with the typical fluctuations of how the building is used. Next, please. So for a few comments towards, and if folks haven't got their questions or comments or thoughts entered yet, please do begin to do so, because we'll wrap after a few slides here. Next slide, please. So we want to talk some about, kind of summing it all up across the reviews we did, the discussions we had with technology vendors, the experiences of our team through prior work, challenges and barriers. Data quality is a really big one. And I would even say in some cases, depending on the specific machine learning method, just data volume. These are very sort of data greedy methods, but lack of high quality data from building automation systems is definitely something we have to grapple with. And I think that's kind of fair, or makes sense, considering that, if we go to principal design intent, those automation systems were set up really to effect consistent, reliable control and maintain set points across the building. And they weren't necessarily conceived nor natively designed as a data collection and acquisition system with the latest and greatest machine learning methods in mind. So that is definitely something to be aware of. The nature of the beast is that model selection and parameter tuning can be a really hairy step in the process, and there's a lot of expertise that can go into selecting models, implementing the right tuning settings for different parameters in these models, and generalizing those from one implementation case to the next. Next, please. Visualization comes up. There's always a question of, if we have if we have methods that are running under the hood that are less intuitive or less familiar to users, then how is it that we can best present those results in our visualizations to help users evaluate and understand specific recommendations or findings that are being generated? We can also say that, we're not at the point ever really of like full autonomy. There's a lot of expert knowledge that's being used to supplement or augment machine learning. This comes up a lot in steps that have to do with verification, validation, and authorization. Specifically, I think that comes up a lot in control. Next, please. A couple of concluding thoughts here. First, it was interesting for us to see just the different opinions across vendors and product providers, difference in opinions as to how much we're ultimately going to gain through AI and machine learning. It seems pretty clear that in this whole process of delivering and developing more intelligent diagnostics and controls, we'll probably be leveraging and pairing new machine learning strategies with those conventional techniques that we've historically relied upon. By that, I mean things like rule-based fault diagnostics or very classical optimization strategies. Machine learning and AI is being talked about a ton. It's like one of the most popular topics for us in sort of building analytics and advanced control these days. It's really just beginning to be incorporated into commercial product space. And the caveat there, right, is this is with the exception of regression, which has been, a really powerful and successful approach across the industry for a very long time. Step outside of regression, and it's really new territory where we don't see as much direct uptake into product yet as the level of discussion might otherwise imply. Finally, I'll say that it's pretty exciting stuff, actually, and there's really clearly great potential, especially when we look to other industries and domains and see how these methods have really transformed the ability to extract new knowledge and understanding out of data. But given that we're so kind of early on, this is going to be validated, and we're going to gain a lot more nuanced understanding of how it all plays out through our collective and ongoing industry and research efforts. Next, please. That's the conclusion of my prepared materials for today. We can open up to your questions, to your comments, and I will ask for Hannah's support in kind of navigating that list of questions that you all submitted.
Thanks, Jessica. That was a great presentation, and we do have a number of questions. So I'm going to kick it off with a very practical question about RFPs. So what's your view of including machine learning in the technical requirements in the RFP for EMIS at this point in machine learning development? And many of you already know on the call that LBNL has a lot of templates to help owners in developing RFPs. I will say that we don't currently have machine learning requirements in the templates, but it comes up as a question of whether owners should specify machine learning in the technical requirements of their RFP.
Yeah, that's a great question. My first sort of gut on that is that, I think of machine learning or AI as more of a tool or what do we say, the means and not necessarily the ends itself. So I would kind of say, a lot of the times we encourage folks to think about functionality and performance as opposed to specifying particular methods to get there. I think fundamentally, if you did, based on kind of what we saw from our review of the product space and the fact that this is pretty nascent, I don't know that there would be a great advantage in terms of, specifying that someone must use a machine learning strategy to deliver a certain type of functionality. And there's a lot of evidence showing that we're getting great savings from this host of analytics technologies, even without machine learning attributes. So I wouldn't necessarily recommend to go straight to requiring it, but rather focus on the functionality and the performance that you want to stipulate. And then we can have the fun of learning, was that delivered through machine learning or some other type of approach?
Great, thanks, Jessica. And kind of a follow-on question to that, what questions should an owner ask to understand a vendor's machine learning approach? I mean, owners may not understand all the details of the different methods. So, how do they go about kind of unpacking that?
It's really important to kind of probe to ask providers to share specifically what methods are being used for which specific types of analyses, using what data as inputs, why perhaps they made those choices versus other techniques that could be implemented that are not machine learning, and if they have any results from having tested and compared or contrasted the machine learning based approach with something more traditional or conventional. I think it's that level of discourse that I think is most informative. And, frankly, sometimes the answer might be, well, it's what we're using now. We haven't done a thorough side-by-side comparison, but we think there's an advantage. But I think that pulling it down to that level of specificity kind of opens up a new plane of discourse that can dig into nuance more, and maybe like a little more transparency or honesty around where we're at in incorporation of the methods and understanding their relative advantages over other techniques we might employ.
Thanks. All right, this one is going towards a little earlier in design. So how do you think methods based on machine learning would change the building design and or retrofit processes in the future, especially early design stage?
That's interesting. So I think there's a lot of potential to use AI and machine learning in design. I'm kind of thinking back to, say, looking at other industries where various, let's say, complex system designer support tools will embed these methods to kind of iteratively come at optimal designs through an expert in the loop type of process. So there could be some fun things there for the buildings industry to start incorporating more pervasively. My expertise is not in design tools necessarily, or I should say is not in design tools at all, more accurately. There's probably also good opportunity for that feedback loop from operations back into design and identification. You could imagine as you amass more data over time, things like being able to better understand what system types and configurations actually pan out best under different circumstances. Looking at many more permutations than we can do today. Thank you for that question.
Thanks, Jessica. Yeah. Through the Smart Energy Analytics campaign, we did hear a lot about that exactly, of learning more about your loads and being able to right-size equipment and that kind of thing from the diagnostics you're doing with your existing operations.
Mm-hmm.
Kind of piggybacking onto that, there's a question about, do you think autonomous buildings are possible eventually? I know you touched upon that we do need humans in the loop. This is not replacing humans. So can you expand upon this potential for autonomous buildings, they say, similar to self-driving cars?
Are autonomous buildings possible eventually? That one, I guess, I don't know, not to be like too Bill Clinton about what's the meaning of the word "the," but it, it kind of, it's like, what do we think that we mean by autonomous? And so, like many things are possible eventually. So I would hate to say like no, but I think to, kind of peel the onion on that a little bit. Autonomous buildings, like similar to self-driving cars, I think the prospect could be a little trickier in that we have a lot more complexity and diversity of systems. We have occupants, and we have that, notoriously kind of fractured delivery process. And ultimately, when things break, we still have to fix them. So even our self-driving cars, still need, we still need mechanics. We need them more and more, actually, as our cars get smarter and smarter, because we can't just fix things in our garage anymore. So I think there's good prospects there. I do think there's huge advances to be made over time, specifically around controls, but I don't think that we're very close to like completely removing accountable parties for operations out of the loop.
Thanks. And through the campaign, we've also heard that the building engineers are just able to find and fix more things. They actually have quite a bit to do. It's not like there's less for them to do as a result of implementing diagnostics.
Yeah. I guess I think, like, I'll just add one more thought to that, which
Sure.
is If we like big picture, there's a heck of a lot of commercial buildings in our stock. And I think rather, in some ways it's like as exciting to think about, not necessarily just full autonomy, but just massive scale at orders of magnitude more than we're able to deliver today. So not like removing humans out of the loop completely, but empowering and enabling the humans to cover so much more territory than they ever could before. And that's also, kind of a different lens into some of that same spirit that I think is motivating that question.
Mm-hmm. Great, thanks. This is a really interesting question about data tagging, basically. So how is image processing potentially used to supplement machine learning processing of data that's obtained through the BMS? So can this be used to help resolve nomenclature patterns when the metadata isn't embedded in the BMS? So like using drawings to add context to machine learning program. So image processing as a way to get those tags into your system.
I think that's a really, great area to think about. Because the reality, like where my mind goes when I hear that question is, and I think thank you for including like the mechanical drawings piece of it, because I'll use, say, fault diagnostics as an example. Some of the early stages in trying to stand up and configure those systems, really get them going, involves this time-intensive crosswalk between understanding mechanical drawings and then single line diagrams and then panel schedules and then say object trees and hierarchies through the front end of the building automation system and connecting all the dots in addition to just understanding some of the point naming conventions. And that starts to speak to some of the broader semantics or understanding the meaning of the data and not just what the data represent, and the context of how they fit into the overall physical system of the building. So I think there's great potential to do that, and not just image processing, but also probably like text and language processing as well.
Thanks. And here's a follow-on question actually to that from a different person around point tagging. So are the point tagging processes in machine learning products standalone? With 70% of the time being spent tagging, it would be great to have a solution that is agnostic to the end tool used for analysis.
Yeah, so the first thing I'll say is the 70-30, that's a comment from a person we talked to. So that's not like, analytically derived or anything, but I think it's a fair enough, kind of order of magnitude estimate. I've not yet seen standalone point tagging products. I know of folks who are working on improving the process, but usually that tends to be coupled with the overarching tool used for analysis, or let's say the tool of trade for a specific provider who's invested in their methods. Now, I want to also acknowledge that, of course, we have things like the haystack tagging convention, and people may choose to implement that convention, and then once the data is tagged and labeled, then that is available to other systems. So as not to confuse, I want to be sure to make that distinction.
Great, thanks. Yeah, it was one of the biggest things when we had these interviews. People were using the machine learning for automating that process, but it was definitely within each individual product. Mm-hmm. Here's a question on data quality. Can you clarify improving data quality? I'm not remembering exactly which slide that went to, but when you deploy a smart application, what data quality challenges arise for you? I know data quality is a huge issue, so.
Yeah. I mean, just a couple of like very straightforward examples. The data we want to use are sometimes not accurate. So we have sensors that drift. Maybe that doesn't matter for, maintaining zone air too much. But maybe it really matters if you're trying to get sophisticated around the analytics that you're using that point for. We have problems with gaps in data. In some cases, you can just skip over or ignore gaps. In other cases, things really break down. Your algorithms and methods don't work. And so then you have to figure out how are you going to fill gaps or interpolate. Outliers can be a problem. We've all seen, anyone who's looked at, say, like a lot of meter sensor data, you get anomalous spikes that are like completely out of range. You're like, what is this? Fine if I'm just visualizing a graph and I can, very quickly skip over that. Something that I have to deal with a little more if I'm modeling against certain features and trying to classify things. Hopefully I gave a couple of examples around common data quality issues and how they might trip up certain types of algorithms or just provide maybe not something that's hard, but like another thing to have to deal with. And so if you're trying to harness, many tens of thousands of data points, that can be an issue when you're moving into things like model predictive or advanced supervisory control. It can in cases be even more problematic than in some of your diagnostic cases.
Great. Thank you so much. We're going to try to squeeze in 2 more questions, and then I know you have some end slides. So on that topic of model predictive control, has model predictive control been deployed successfully in HVAC control and optimization?
That's a big question. And I actually don't think that I have more slides.
Well, there are some on future webinars and things. So yeah, like wrap up.
Oh, okay. Maybe I didn't know that. Great, thank you. Model predictive control. Okay, so out of the whole like panoply of technologies that are out there, this is certainly the most emergent and the place where industry, like there's a heck of a lot more FDD or meter analytics solutions out there than there are predictive control optimization solutions. So I'll start there. I think we're really actively exploring and testing and validating what the performance of those different techniques are. It's also a huge component of ongoing research and development, where in those contexts, some things are successful and other things prove challenging, and we're still working on it. So what I would like to say there is that what's exciting and on the horizon for model predictive control is that we're really moving, like we know that we want to get to a future where buildings are dynamically responsive and moving beyond like a single set of sequences of operation that maybe we modify as we move into a swing season or a different season. We're really looking at every day, how are we going to control the systems? We have desires to dynamically change building loads to be grid interactive, to accommodate occupant preferences, different comfort needs, to really just become kind of more flexible in how we control buildings and deliver building services to occupants. And health is coming even more into the picture now, as is a big trend in our industry of thinking about how like low energy versus low carbon, bringing in a whole slew of different sort of time of day and utility mix considerations. So my point being that um, as soon as we move outside of sort of wanting to do um, annual minimization of total energy use into a realm where we have multi-objective optimization, we might have price response, we might be really aiming to do quite a bit more, then I really believe that you need the model predictive control to do that. And so that's why it's so important for us to continue working on it, and why I remain very optimistic to see commercial products becoming available.
Great.
I hope I
Okay,
answered.
we're going to squeeze in. That's, yeah, excellent. Thank you for that. And we're going to squeeze in one more question. It's a really great question. How can we get ground truth data for training our machine learning models? For example, unfaulted and faulted data is a really important question.
Great. I feel like I just that's, we're actually, working on this right now at a project. So I'm going to say it's not just my team. My team at Berkeley Lab has an ongoing multi-year effort to create large test data sets that in fact do have that ground truth labeling of faulted and fault free, and contain a lot of the common measurement points that our FDD algorithms would be looking to access from the BAS to exercise their logic over. So we're actively working on that. Anyone interested, please follow up with me directly. And I'm really excited to say that it's not only the efforts of our team, but folks involved at other institutions, universities, both domestically and internationally. So I'm really looking forward to building up a big head of steam there so we can provide that resource back to the development community, whether it's research kind of development or commercial product development. Thank you for the question.
All right, I think going to the next slides to wrap up with the future webinars would be great now.
Okay, next steps, please register for upcoming webinars. It looks like we've got two coming up, both in the month of October. So October 8th, results, this will be a good one. Results from New York State's real-time energy management program, very forward-looking, innovative incentive programs there. And second, very near and dear to our heart, final results on savings, costs, and benefits from the Smart Energy Analytics campaign. That will be Wednesday, October 28th. Please do join us. And thank you for attending today. Thank you for your attention and the great questions. Contact Better Building Alliance to learn how you can get involved with our energy management and information technology team. Led by the team here at Berkeley Lab, collaborating with researchers and industry experts and building owners to promote awareness and savings through new technologies. I believe that concludes our webinar. Thank you, everyone.